So yesterday we looked at stationary points and how to find them. So now today we're going to look at the different types of stationary points. It's pretty straightforward. There's 3 different types. The first one is if your stationary point is here, like at the top of a peak, then we call it a local maximum. So what's the gradient on the left-hand side of the local maximum? Positive. And the gradient on the right-hand side? Negative. So if you know that you've got a stationary point and on the left side of it, it's a positive gradient, and on the right side of it is a negative gradient, you know that that stationary point is a local maximum. If you've got one that looks like this and your stationary point is at the bottom, we call it a local minimum. So again, the gradient on the left-hand side is now negative. The gradient on the right-hand side is positive. And the other type is if you've got a graph that goes like this. Obviously, a stationary point is when the gradient is 0, so right in the middle there. Or also if it goes down like that. So the gradient on this side would be positive and then still positive. And then for this one, it'd be negative and then still negative. And we call those stationary points of inflection. Just like when we did cubics and they were just called points of inflection, then now we know that they're called stationary points of inflection. So all you've got to do is find your stationary points when the gradient equals 0. And then you've got to look on either side of the stationary point, determine what kind of gradient it is, and that will give it away what kind of stationary point it actually is. Okay, so our example is y equals 3x cubed minus 4x plus 1. And we have to find the stationary points and state their nature. So is it a local max, a local min, or a stationary point of inflection? So when we were looking for the stationary points, what was the first thing we did? Yeah, you derive the function because you're looking for when the gradient equals 0. So we're going to do dy dx. What's the first term? 9x squared, good. Then? That's it. Okay, so we know that they're stationary points when the derivative equals 0. So we'll make this equal 0. Right, and solve for x just by rearranging. So of course we're just going to take our 4 over, going to divide by 9, and then take the square root, and of course it's plus or minus. Right, how can we simplify the square root of 4 on 9? Yeah, so it's the square root of 4 on the square root of 9, so that is plus or minus 2 on 3. So we've got 2 x values. What are we going to do with those 2 x values? Sub them in one by one, find the corresponding y values. So we'll deal with the positive first. So we've got y equals 3 times 2/3 cubed minus 4 times 2/3 plus 1. Right, 2/3 cubed, what's that? What do we do when a whole fraction is taken to the power? Yeah, so we cube both the 2 and the 3, so 8 on 27. Minus, times it across to the top. So times it to the top, we get 24 on 27 minus 8 on 3 plus 1. Now it's just a case of adding fractions together. So simplify the first fraction. What do you get? What can you divide both of those numbers by? 3. Yeah. 3 will work. So we divide by 3, we get 8 on 9. Let's change this to on 9. So we're going to times the top and bottom by 3. And then make that 3 on 3. Sorry, no, 9 on 9. What am I doing? Nine on 9. Okay, we know that's going to be on 9. 8 plus 9 minus 24. So 8 and 9 make 17. Take 24. Get negative 7. Wait. Oh, wait. Why do I have a... yeah, so 7. So that's the point. Sorry, yeah, negative 7. Good pickup. So that's that point there. Now, of course, we have another x value, so we need to work with that one as well. So y equals 3 and negative 2/3 cubed minus 4 times negative 2/3 plus 1. Right, it's going to give us the same values, but the first one, because it's cubing a negative, it's going to be negative. So we know that it was 24 and 27, so we can say negative 8 on 9 plus 24 on 9 plus 9 on 9. So we already did the exact same fraction work, so there's no need to do it all again. You just know that the first term is a negative. So now we got 9 minus 8, which is 1. Yeah, so this should be 25 on 9. So we've got the point negative 2/3 and 25 on 9. Right, so those are our two stationary points. This one here and this one here. Right, now we need to figure out what type of stationary point they are. What's their nature? So we're going to test what's on the left-hand side and the right-hand side of either point. So if we've got like our x, this is 0, this is 1, this is negative 1. Right, our 2 on 3 would be like here, there, and negative 2 on 3 would be like here. So, well, we need to figure out what's on either side. So how about we test x equals negative 1, x equals 0, and x equals 1. Find the gradient when x equals those. So how do we find the gradient when x equals negative 1, 0, and 1? Yeah, sub them into the derivative. Yeah. Try and squish it in. So we're going to find the derivative when x equals 1. So we're using this derivative here. 9 times 1 squared minus 4 equals 9 minus 4, which is 5. So that's a positive gradient. Then 0 is 9 times 0 squared minus 4, which is negative 4. So that's a negative gradient. And then we've got when the gradient when x equals 1, 9 minus, sorry, that should be a negative in there, but doesn't make it any different. 4, so we get 5. So that one's positive. So looking at our gradients, we start with a positive gradient, so it'll be going up that way. Then you'll have the first stationary point, that was this one. Then you've got a negative gradient, and then you've got the second stationary point, which was this one. And then you've got a positive gradient. So you can see straight away that this one here is a local max, and then this one here is a local minimum. That's pretty much all there is to it.
And then how do you determine the inflection one?
Because you'll have like a positive and then a positive on either side, or a negative and then a negative.
Oh, okay.
Yeah. So you know, if it goes negative, stationary point, negative, then that's a point of inflection. Stationary point of inflection. Or if it goes at positive, stationary point, positive, then it's like, it's that one and this one.